NEMAST students. The NEB 2083 board exam is just around the corner, and are you ready to tackle the unit with the highest marks? That's right, electricity. In this quick 20-minute video, we will master the 4 most important chapters: electrical circuits, magnetic field, electromagnetic induction, and alternating currents. For each chapter, we'll cover all the key concepts, list every single formula you need to memorize, and solve important NEB past paper numericals. Stay focused, because mastering these chapters can help you secure over 20 marks in your final exam. Let's begin. Hello students. Welcome back to our final exam revision. Today, we're diving into one of the most high-yield chapters for your NEB exam, Chapter 14, Electrical Circuits. Get ready to master the flow of current and solve some key problems. Let's do a rapid recap of the core concepts. First, we have Kirchhoff's laws. The junction rule, or KCL, states that the total current entering a junction must equal the total current leaving it. The loop rule, or KVL, states that for any closed loop, the sum of the electromotive forces equals the sum of the potential drops. Next, the Wheatstone Bridge principle gives us a condition for a balanced bridge where no current flows through the galvanometer. This principle is practically applied in the meter bridge to find an unknown resistance. Then we have the potentiometer, a versatile instrument used for accurately comparing the EMFs of 2 cells and for measuring the internal resistance of a cell. Finally, remember galvanometer conversions. To make an ammeter, you connect a low resistance, called a shunt, in parallel. To make a voltmeter, you connect a high resistance in series. Now for the formulas you absolutely must know. For Kirchhoff's current law, the sum of currents at a junction is 0. For his voltage law, the sum of EMFs equals the sum of IR products in a closed loop. The Wheatstone Bridge balance condition is P over Q equals R over S. For the meter bridge, the unknown resistance X equals R times L divided by 100 minus L. The potentiometer has 2 key formulas for comparing EMFs, E1 over E2 equals L1 over L2. And for internal resistance, small r equals capital R times L1 minus L2, all divided by L2. For converting a galvanometer to an ammeter, the shunt resistance S equals Ig times G divided by I minus Ig. And for a voltmeter, the series resistance R equals V over Ig minus G. Memorize these. Let's solve a classic NEB question. The problem states, a galvanometer of resistance 100 ohm gives full-scale deflection at 10 mA. How can it be converted into an ammeter of range 0 to 1A? Calculate the value of the shunt resistance required. First, let's list our given values. The galvanometer resistance, capital G, is 100 ohms. The current for full-scale deflection, Ig, is 10 milliamperes, which we must convert to 0.01 amperes. The desired maximum current of the ammeter, capital I, is 1 ampere. The conversion requires connecting a low-resistance shunt in parallel with the galvanometer. The formula we need is S equals Ig times G divided by the quantity I minus Ig. Now we substitute the values into the formula. S equals 0.01 times 100, all divided by 1 minus 0.01. The numerator becomes 1. The denominator becomes 0.99. So, S is 1 divided by 0.99. Calculating this gives us a shunt resistance, S, of approximately 1.01 ohms. So, our final answer is, to convert the galvanometer into an ammeter of range 0 to 1 ampere, a shunt resistance of 1.01 ohm must be connected in parallel with it. Finally, some quick exam tips. A very common mistake is messing up the sign convention while applying Kirchhoff's loop rule. Practice it well. NEB frequently asks numerical problems from galvanometer conversion and potentiometer applications, so master those. Always draw a neat, labeled circuit diagram for your numericals, even if the question doesn't ask for it. It helps clarify your thinking and can fetch you partial marks. And remember to convert all units to their SI base units, like we converted milliamperes to amperes, before you start calculating. Good luck! Namaste students, and welcome back to our NEB Final Revision series. Today, we're diving into one of the most exciting chapters in physics, Chapter 16, Magnetic Field. Alright, let's do a super fast recap of the key concepts. First, we have the Lorentz force, which is the fundamental force experienced by a single charge moving through a magnetic field. When you have many charges moving together, like in a wire, you get the force on a current-carrying conductor. Now, if you bend that conductor into a loop or a coil and place it in a magnetic field, it experiences a turning effect, which we call torque. To calculate the magnetic field itself, we use two powerful laws. The Biot-Savart Law helps us find the magnetic field from small current elements, and we use it to find the field at the center of a circular coil. For situations with symmetry, we use Ampere's Circuital law, which is great for finding the magnetic field inside a solenoid. Finally, we look at the interaction between two parallel conductors they attract if currents are in the same direction. And don't forget the Hall effect, which proves that the charge carriers in a conductor are indeed negative electrons. Now for the essential formulas you must know. The Lorentz force on a charge is given by F equals QV sine theta. The force on a straight conductor is very similar, F equals BIL sine theta. The torque on a rectangular coil with n turns is tau equals NBI sine theta. From the Biot-Savart law, the magnetic field at the center of a circular coil is B equals mu naught Ni divided by 2R. For a long straight conductor at a distance d, the field is B equals mu naught I divided by 2 pi d. Inside a long solenoid, the magnetic field is uniform and given by B equals mu naught small n I, where small n is the number of turns per unit length. And the force per unit length between two parallel conductors is F over L equals mu naught I1 I2 divided by 2 pi d. Memorize these, they are your best friends. Let's solve a typical NEB numerical. The question is, a straight conductor of length 0.5 meters carrying a current of 2 amperes is placed in a uniform magnetic field of 0.1 Tesla perpendicular to the conductor. Find the force experienced by the conductor. Okay, first, let's write down what we are given in the problem. The length of the conductor, L, is 0.5 meters. The current, I, is 2 amperes. The magnetic field strength, B, is 0.1 Tesla. The problem also states that the field is perpendicular to the conductor. This means the angle, theta, between the conductor and the magnetic field is 90 degrees. Now, we need to choose the right formula. We are looking for the force on a current-carrying conductor, so the formula is F equals BIL sine theta. The next step is substitution. We just need to plug in the values we have. So F equals 0. 1 times 2 times 0. 5 times sine of 90 degrees. We all know that sine of 90 degrees is exactly 1. So the equation becomes F equals 0. 1 times 2 times 0. 5 times 1. Finally, we calculate the result. 0. 1 times 2 is 0. 2 and 0. 2 times 0. 5 is 0. 1. So F equals 0. 1. Therefore, the final answer is, the force experienced by the conductor is 0.1 newtons. To score full marks in this chapter, here are my top tips. First, master your right-hand rules. Fleming's left-hand rule for force and the right-hand grip rule for field direction are crucial. A common mistake students make is forgetting the sine theta term in the force and torque equations, especially when the field is not perpendicular. So always check the angle. Finally, for the NEB exam, be prepared for both short numericals, like the one we just did, and derivations, especially for the magnetic field of a long straight wire or inside a solenoid using Ampere's law. Practice those derivations well. Good luck! Hello everyone and welcome back. Today we tackle a hugely important chapter for your NEB exam, Chapter 18, Electromagnetic Induction. This is where we see the beautiful connection between magnetism and electricity. Let's get started. Alright, a quick recap of the core ideas. First, we have Faraday's laws of electromagnetic induction. These laws state that a changing magnetic flux through a coil will induce an EMF. The faster the change, the greater the EMF. But which direction does the current flow? That's where Lenz's law comes in. It says the induced current creates a magnetic field that opposes the original change in flux. Next up is motional EMF, which is generated when a conductor moves through a magnetic field. This is the core principle behind the AC generator, a device that brilliantly converts mechanical energy into electrical energy. We also have eddy currents, which are unwanted circulating currents induced in bulk conductors. Finally, remember self and mutual inductance. These concepts describe how a coil resists changes in its own current or induces a current in a nearby coil. This is the magic behind the transformer used to step up or step down AC voltage. Now for the tools of the trade, the formulas. The most important one is Faraday's law, which mathematically is EMF equals minus N times d phi b by dt. The minus sign represents Lenz's law. For a straight conductor moving in a field, the motional EMF is simply EMF equals BLV. For an AC generator, the induced EMF varies with time. Its expression is EMF equals NBA omega sine omega t. The self-inductance of a long solenoid is given by L equals mu naught N squared L, where little n is turns per unit length. The mutual inductance between two coils is M equals mu naught N1 N2 A over L. To find the energy stored in an inductor, we use E equals 1/2 Li squared. And for our transformers, the crucial transformer ratio is Vs over Vp equals Ns over Np equals Ip over Is. Remember this one. Let's solve a typical NEB past paper question. The problem states, the magnetic flux through a coil of 100 turns changes from 0.02 Webers to 0.06 Webers in 0.1 seconds. Find the induced EMF in the coil. Okay, first step is to list the given values. We are given the number of turns, N is 100. The initial flux is 0.02 Webers, and the final is 0.06 Webers. The time interval, dt, is 0.1 seconds. Now, let's find the change in magnetic flux, which is d phi. This is simply the final flux minus the initial flux, 0.06 minus 0.02, which equals 0.04 Webers. The formula we need is Faraday's law of induction. We are looking for the magnitude, so we can write EMF equals N times the absolute value of d phi by dt. Now we substitute our values into this formula. We get EMF equals 100 multiplied by 0.04 divided by 0.1. Let's simplify the fraction first. 0.04 divided by 0.1 is 0.4. So, our equation becomes EMF equals 100 times 0.4. This gives us a final answer of 40. Therefore, the induced EMF in the coil is 40 volts. It's that straightforward if you follow the steps correctly. To score maximum marks in this chapter, here are my top tips. First, truly master Lenz's law. It's the key to all conceptual questions about the direction of induced current. Second, always watch your units and be consistent. The NEBs loves to ask about the working principles and energy losses in transformers and the AC generator, so prepare those theoretical questions well. A very common mistake students make is forgetting the number of turns, N, when using Faraday's law. Don't let that be you. Remember these points and you'll do great. NEMAST students, welcome back to our final revision. Today we are jumping into a very important chapter. Get ready for Chapter 19, Alternating Currents. Let's begin. Alright, a quick concepts recap. Remember, AC voltage and current are constantly changing. We measure them using RMS, or root mean square values, which is the effective DC equivalent. The peak value is the maximum amplitude. When AC passes through a pure resistor, voltage and current are in phase. In a pure inductor, voltage leads the current by 90 degrees. In a pure capacitor, current leads the voltage by 90 degrees. We visualize these phase differences using phasor diagrams. For a series RLC circuit, their combined opposition is called impedance. At a specific frequency, called the resonant frequency, the inductive and capacitive reactances cancel out, minimizing impedance and maximizing current. This is resonance. The sharpness of this peak is measured by the quality factor, or Q factor. Finally, the power factor tells us how much power is actually used, and a choke coil is an inductor used to control current efficiently, with minimal power loss. Now for the formulas you must know. First, relating RMS and peak values. The RMS voltage Vrms is the peak voltage V0 divided by √2. Same for current. Next, reactance. Inductive reactance, X sub L, is omega L, which equals 2 pi FL. Capacitive reactance, X sub C, is 1 over omega C, or 1 over 2 pi FC. For a series RLC circuit, the total impedance Z is the square root of R squared plus the quantity X sub L minus X sub C, all squared. The resonant frequency, F0, is 1 over 2 pi times the square root of LC. We find the phase angle phi using tan phi equals X sub L minus X sub C, all divided by R. The power factor is simply cosine of phi, which also equals R divided by Z. And finally, the average power dissipated is P equals Vrms times Irms times cos phi. Let's solve a typical NEB numerical problem. The question is, an LCR series circuit has R equals 100 ohm, L equals 0, 5 Henry, and C equals 10 microfarad. Find the resonant frequency and the current at resonance if the applied voltage is 200 volts. First, let's list our given values. We have resistance R as 100 ohm. Inductance L is 0, 5 Henry. Capacitance C is 10 microfarad, which we must convert to farads. That's 10 times 10 to the power minus 6 farad. The applied RMS voltage is 200 volts. The first part asks for the resonant frequency, F0. The formula for resonant frequency is F0 equals 1 divided by 2 pi times the square root of LC. Let's calculate the LC product first. L times C is 0. 5 times 10 to the power minus 6. This gives us 5 times 10 to the power minus 6. Now, we take the square root of LC, which is the square root of 5 times 10 to the power minus 6. This comes out to be 236 times 10 to the power minus 3. Now we plug this back into our frequency formula. F0 is 1 divided by, in brackets, 2 times 3. 416 times 2. 36 times 10 to the power minus 3. After calculating, we get the resonant frequency as 71. 2 Hz. That's our first answer. The second part asks for the current at resonance. A key thing to remember is that at resonance, the circuit's impedance Z is at its minimum and is equal to the resistance R. So Z equals R, which is 100 ohm. Now we can easily find the current using Ohm's law for AC circuits, I equals V divided by Z. So, the current is 200 volts divided by 100 ohm, which equals 2 amperes. So, our final answers are, the resonant frequency is 71. 2 Hz and the current at resonance is 2 amperes. Finally, some quick exam tips. NEB loves asking for the derivation of the impedance formula for an RLC circuit using a phasor diagram, so practice that. Numericals on resonance, like the one we just did, are also extremely common. A common mistake is forgetting unit conversions, like microfarads to farads, or mixing up peak and RMS values. Always double-check your givens. Focus on phasors and resonance conditions and you will score well. Good luck. Alright everyone, that's a wrap. Remember these key formulas: shunt equals Ig times G divided by I minus Ig. Force on a conductor is F equals BIL sine theta. Faraday's law, EMF equals minus N times the rate of change of magnetic flux. And resonant frequency, F0 equals 1 over 2 pi times the square root of LC. If this video helped, hit subscribe and like this video. Drop a comment telling me which chapter you want a deep dive on next. Coming up, Optics One Shot for NEB 2003. Stay tuned.